Hello there, and welcome to this video session, a question and answer with me, Geology Professor Shawn Willsey. We're going to mainly be focusing on the situation in Iceland, but a few of the questions that we have for today are more of a broad nature and applied to just geology in general. So before we get started, just a quick update. Today is November 21st, but yesterday in my November 20th update, we had a lull in earthquake activity, and it's since come to my attention that they're experiencing a pretty strong storm there in Iceland, and the wind and the rain and the elements actually typically hamper the ability to detect really sensitive and small earthquakes. And so we might be seeing that as a result of that. So I just wanted to put that out there as a small little correction. What I'd like to do before we get to some of the questions, though, is start off with a little lesson on magma just in general. And some of you may know this may be new to others of you, but there's been enough questions about the magma and the volcanic activity that I think it's worth going back and looking at some of the basics and the fundamentals regarding magma, exactly what it is, how it behaves, the different types of magma. So if you'll indulge me for a few minutes, we'll start there. And this is right out of some material that I teach in my class. And so you guys are getting college level geology here just right off the bat. So we use these terms somewhat interchangeably, magma and lava, but they do have a clear distinction in terms of volcanoes and geology. So magma is what we call molten rock that lies below the surface, and lava is what we call that material once it reaches the Earth's surface. The other big distinction here is I think a lot of people treat this molten rock material, magma or lava, they treat it like it's liquid rock. And it's not just that. It's actually crystals that have already started to form in the magma, the liquid rock itself, which we sometimes call melt, and then dissolved gases in it. So it's really quite an interesting material because it contains both solids, liquids, and gases all together. And then the other important thing is the proportion of any one of these three components can change from location to location and from time to time. So you might have a magma body that is initially hotter and more molten and has a more liquid or melt component to it, but as time goes by, it might develop more crystals in it. So its proportion goes up to some degree. You might also have times when there's more or less gases. So hopefully that helps a little bit there. The other distinction between magma and lava is even though it feels like it should fundamentally be the same and it's just what we call it above and below the Earth's surface, remember that when that magma makes its way to the surface, a lot of the gas is released. So a lot of the gas in a lot of volcanoes, the gases can escape. And so magma usually contains a lot more dissolved gas in it because that's underground and it's trapped. Versus when it's at the surface, a lot of that gas is going to rise because it's less dense and escape the lava. Sometimes it gets trapped and you see little bubbles in the lava. But that's another important distinction there. And then the other term that's important when understanding magma and lava is this term viscosity, which is basically resistance to flow. It's the opposite of fluidity. So water, for example, is a highly fluid material, but it has a very low viscosity. It's very fluid. So if something has a high viscosity, it doesn't flow very readily. It resists flow. It doesn't go very fast. So an analogy I like to use in class that works pretty well is something like honey. So honey, as you probably know, when it's at colder temperatures, it's very sluggish and stiff and sticky, pasty. And then if you heat up the honey, you can get it to behave more fluid. And so the viscosity of that material changes with temperature, just like the oil in your car. Its viscosity changes with temperature. There's all sorts of analogies we might propose that are related to that. The other interesting thing, honey is another good example because, as many of you know, honey, when it sits for a long period of time, it will have a tendency to crystallize. And magma does much the same thing. And so remember that there's this important connection between both temperature and something we're going to call silica content. And you can think of silica content for now as being crystals in the material. So if we have a high temperature magma or lava, that means it's low viscosity. It flows very readily. These are the types of lava flows that you see a lot of times in Iceland, In Hawaii, these are the tourist-friendly eruptions, right? When lava has a low viscosity, generally it's something you can observe from a fairly close but safe distance, and it's just awesome. Okay. If magma though has low temperatures, so if it's a much lower temperature material, it will be a lot more stiff and sticky. Again, just like the honey. And so the magma and the lava at low temperatures with high viscosity, it's going to trap the gases. The gases they can't move as easily through the material. They don't have as much mobility. And so that could trap the gases. And ultimately, you could create a situation where the gases are trapping or getting trapped in the lava or magma to such a degree that it's increasing the internal pressure and possibly culminating in an explosive eruption. And then silica has a similar relationship with viscosity. When we have a lot of silica in the magma or lava, that results in a very high viscosity material. So it's going to be stiff and sticky. It's not going to flow very well. On the flip side, if it's low silica, it's going to flow very easily. And again, for now, I think the easiest way to think of these is just think of them as crystals, right? The more crystals, high silica, high crystal content, it's going to be more sluggish, just like your honey when it starts to crystallize. Low silica or low crystal content, it's going to behave a lot more fluid over time. So hopefully that helps a little bit, maybe clarify a few things. The other thing here, and we don't need to get into this in too much detail, but we do have different types of magma then, so it should stand to reason through various processes that we won't get into here. The Earth generates magma, but magmas come in different compositions dictated by how much silica they have. So at one end of the spectrum, we have basaltic magma, which is very low in silica overall. It's about 50%. Therefore, it's very low viscosity. So these types of magmas tend to be hotter. They tend to behave more fluid-like when they erupt. They tend to not trap as much gas because of their viscosity, and so their explosiveness is very much reduced. Now, you can get basaltic magmas behaving more explosively if they're interacting with water, but that's a totally different topic. Let's just focus on land. Basaltic magmas in general are going to produce volcanoes that do not trap gases, produce mainly lava, erupt more frequently over time, like we see in Iceland or Hawaii. And so that's one end of the spectrum. At the other end of the spectrum, if we have a lot of silica in that magma, that's what we call a rhyolitic magma. So the resulting rock type would be a rhyolite as opposed to a basalt. These types of magmas have a lot of silica, so appreciably higher amount of silica, meaning that it's much more viscous and sticky. The gases get trapped in it. It doesn't flow very well. The gases build and build and build, and then ultimately you end up with some much more explosive eruption. These types of volcanoes, thankfully, don't erupt as often or nearly as frequently. A good example of this would be the Yellowstone eruptions, is something someone knows. And then in between the two, and there's other types. This is highly simplified. There's more than just 3 types of magma, but at this level, this is a good way to start with it. And then we have something called andesitic magma that produces a rock called andesite. So this would be something in between in terms of silica composition, not quite as runny as a basalt, but not quite as sticky and stiff as a rhyolite. So in between compositions there. And these can produce both lava flows and explosive eruptions. So this would be like your Mount St. Helens type of volcano. So hopefully that helps a little bit. I just wanted to provide a little bit of background on magma, because as we get to our viewer questions, a lot of those questions relate to magma and magma behavior. So let's just jump right in. Oh, I do have one other thing I wanted to show, a quick little video here. Some of you have probably seen videos of lava erupting and volcanoes and that, but I have a fun little video here. This is in Hawaii in 2014 when I took a group of students out to the eruption site in the East Rift Zone. And this is a video of me. Let me turn the volume down so I can talk over it. This is just a video of me collecting a sample of lava on my rock hammer. But the main point here is to kind of get you an idea of how this looks in terms of viscosity. Now, this lava flow, to be totally transparent here, this lava flow had moved several kilometers away from the vent. At this point, it's lost most of its gas. Most of its gas has escaped. This is a basaltic lava flow, so it's just pooling up in these low areas. It's not on much of a slope. It's cooling on the surface, and so you can see that the glow there is kind of along the margin. And then when I break through with my rock hammer, I break through that that elastic skin or rind on the surface of the lava flow, and then that reveals the hotter, more incandescent lava that's just beneath it. And so this would be, even though it might look kind of stiff and pasty to you, in the world of lavas and magmas, this is still considered a very low viscosity lava flow. You can see how smooth the surface is there of this flow, where it's forming these lobes and these little channels and forms in here. So anyway, just kind of a fun little video collecting a chunk of lava. I'm even going to pick it up here with my hands, which might shock some of you. All I have on there are just simple garden gloves and a long sleeve shirt, some protection from the heat. And that very rock right there is the same. If you look at the webcam here, there's that same rock. So this is my baby basalt, my lava rock that was born in 2014. So this little rock's 9 years old. Pretty sweet. So one of my treasured geologic possessions. But the main purpose of that was to show you a little bit more behavior of that magma or lava. So let's get to the questions here. And again, I tried to pick just a few. There's way more questions coming in than I can answer, so I apologize that I'm not answering all of them. I just don't have the time right now to go through hundreds of comments on all these updates, which right now are happening more or less every single day, and answer those. So if I haven't answered those, I apologize, but I am going to try to answer a couple here. So, and we may go back to Google Earth. So mainly this will just be a discussion that hopefully will be engaging for you. I might use a few visuals, but I don't have any huge, awesome slideshows prepared for these. So let's start with Sharon's question. What are the geological features that result in the formation of a cone volcano versus I think she meant magma eruption over a series of places on a rift? So I think her fundamental question there is, why would we end up getting a cone-shaped volcano versus what we're seeing here in Iceland with these last few eruptions, where we get a rift, if you will. She's calling it a rift. It's a great question. Most volcanoes are what we call central vent eruptions. So the magma comes out of one centralized location. Think of like a simple plumbing system, directing all that magma to the surface. It erupts either lava or ash, whatever material it erupts. That material can accumulate around the vent, and that will build up that cone shape volcano. Now, it might be a big stratovolcano if it's more explosive. It might be a shield volcano, which is a very kind of low profile, almost flat-ish volcano formed by runny lava. If we have a fissure eruption, so if it's erupting along a crack or a fracture that's formed above a dike, or the propagating dike that's come up, then we'll get what we, like I said, what we call a fissure eruption, and that's what we've seen in Iceland. So it really has to do with the plumbing system as that magma gets closer to the surface. Is it erupting along a crack? Then we're going to get a fissure eruption. Or is it erupting through one centralized vent? Now, a lot of fissure eruptions start out, as these big eruptions along a crack, but then over time, parts of it get clogged, and it will sort of centralize into one specific vent there. So hopefully that helps a little bit. Good question, Sharon. From Thomas Myers. If this, referring to the Iceland situation that's ongoing, turns out to be a non-eruptive event, how long until the magma is cool enough to reoccupy the town? Would this new hardened magma layer make it harder for future eruption through this new rock layer? Yeah, great question. So I think like if everything just stops right now, like the earthquakes die down, the ground deformation dies down for a year or whatever, for in the foreseeable future, the magma cooling would not be, I think people would be back in town way before the magma has cooled, because magma takes, sometimes it depends on how big the magma body is. If it's a really large magma chamber, what we might call a pluton or batholith, it has, it's tens or maybe hundreds of kilometers across in diameter. Those magma bodies can take hundreds of thousands of years, even a few million years to completely cool and solidify. In this case, we're looking at magma that's, for the most part, as far as we can tell, moving through fairly narrow planar or tabular features, dikes, sills, and so those aren't nearly as thick, and so those will cool quicker. So we're probably looking at, but we're still looking at years to decades, and maybe, yeah, like maybe hundreds of years for that magma to completely solidify. Rock is a really good insulator, and so the rock underneath this area that we've been focused on the last few weeks will stay hot for quite some time. Um, so I think before that happens, they might reoccupy the town if the seismic data goes down, if the ground deformation goes down. Um, but this would not be necessarily the indicator you would use. And with that, so let's assume that magma now is completely solidified and cooled and crystallized. If we were to have a future event in the area, those rocks probably would be harder because they've cooled underground. And so they're more dense. They don't have the textures and characteristics that make them weak. And so if we had more magma at a future time, it would probably break through some other area. So it probably would not try to reoccupy the place that we're seeing that's active now. So good question. From MT Stingray, about how long of a time frame are we talking about before the magma in the system below to cool and solidify in the event that it doesn't break out and continues filling with more magma? So similar question. I would imagine how good it is at insulating itself in a subterranean environment would allow it to hold its heat for a good amount of time, several months, several years. Yeah, so similar question as the previous one. To cool and solidify in the event that it doesn't break out. Oh, I see. This is a little bit different question though. So how long till this magma, how long do we have to wait till the magma cools enough that it doesn't break out? And so really it gets back to what we talked about at the beginning with the magma being composed of both crystals, gas, and the liquid portion. Some geologists even refer to magma once it has a lot of crystals in it, we sometimes almost refer to it as a crystal mush. Think about when you've seen, what's a good analogy? Maybe water that has a lot of ice in it is kind of slushy, right? Maybe you step in that off the sidewalk in the wintertime and your foot gets a little wet because it's mostly ice, but it has some water in it. Think of that kind of as the magma now, where it's got a lot of crystals, a lot of solids, but there's the liquid portion as well. So you can get to a point where magma contains enough crystals in it that it's probably, we could consider it non-eruptible, right? It's crystallized to the point where there's not enough liquid component and buoyancy, because the crystals tend to be more dense and heavy, and they'll tend to sink to the bottom of the magma chamber. So they'll tend to sink. The liquid might make its way above. You can't actually separate the two completely. Yeah, so lots of variables there. I don't have a really succinct answer to your question. It depends on lots of things. Depends a lot on the gases involved, how much dissolved gas is in the magma. That will provide the buoyancy. But the crystals and the gas don't go well together. The gases need to reside in the liquid portion of the magma, and they'll provide the buoyancy for that liquid portion. So good question. Hopefully I did an okay job explaining and addressing that. Jeannie Champagne, this is a very uneducated question. Is magma in the center of the Earth? Since all large land masses were made from magma, is magma under all land mass with or without a volcano? So that's a good question. Magma is not at the center of the Earth. It turns out as you go down into the Earth, it does get hotter, but the pressure also increases. So you reach a point at which the pressure is the bigger factor there, and that material in the earth can only exist as a solid. So basically, if you were to drill down at any location on the earth, you'd actually be going through mostly rock. There are some places where you might have some magma. There's also an area further down in the earth called the asthenosphere, which is where a lot of magma gets generated, but even that is still considered a solid. It's just a very weak solid. It's an area where it's not a liquid, but it's a very weak material that can generate magma. And then if you get way into the planet, down into the core or the lower mantle, the lower mantle is solid rock under a lot of pressure. The outer core, we think, behaves like a liquid because of the way earthquake waves travel through it. Remember, we haven't been there, so all our information about the the deep interior of our planet is indirect evidence. It's like taking a x-ray of your body and getting an idea of what's going on. So it's imagery. It's not actually going in there directly. And then in the very center of the Earth, the inner core, that is solid. We believe that's solid based on modeling and the behavior of seismic waves, things like that. Since all large masses were made from magma is not under all land masses. So if you just went to the middle of Asia and drilled down, 100 kilometers or more, there's no magma down there. So magma is only located where we get one plate diving beneath another. That's what we call a subduction zone, where plates are splitting apart, like we have in Iceland at a divergent plate boundary, and in these anomalous places like Hawaii and Yellowstone, where there's plumes of magma coming up out of the mantle and coming up towards the Earth. So most of the interior of the planet is not magma. Good question. Hopefully that helps your understanding. Meredith in Sierra, ABC News said the Iceland eruption will be magma but not involve ash clouds. That's most likely true. Also, you explained how the Krakatoa eruption was very different from what's projected to happen in Iceland because it's a different kind of volcano. Yes, because it's a different magma body. The reason why Krakatoa and Iceland are totally different is two main things. They are two different tectonic settings. Krakatoa is at a subduction zone where one plate is diving beneath the other. Iceland is at a divergent plate boundary that's also a hotspot. And so those two settings produce very different types of magmas, and those magmas erupt very differently. So how can you tell what kind of volcano and what kind of eruption this will be, and what are the other types of volcanoes? Please don't use the beach balls to explain this because I don't understand the beach balls. That's great. That made me laugh. So yeah, if you don't know what she's talking about, we had a lesson on one of the previous updates about these earthquake lower hemisphere sphere things called focal mechanism solutions, but they're informally called beach balls. Kind of a deep dive, a little bit technical. If you got it, great. If you didn't, that's okay. So we can tell what kind of volcano we're going to get here in Iceland because we can look at all of the eruptive products on the Reykjanes Peninsula. So as we cruise around this entire region of Iceland, everything we see, all the evidence of past eruptions shows us that it has been dominantly a basaltic eruption. And definitely we see that with the last three eruptions here, 2021, 2022, 2023, in this part of Iceland. So when we look at the rocks and get the ages of the rocks and what kinds of materials they are, that shows us that this is erupting basalt, and almost exclusively basalt in this part of Iceland. And so that helps us know and understand a little bit about how these volcanoes have erupted. We can even look at places like this where we see these little cinder cones and spatter cones, and we can see the big lava flows that came out of them. So that lets us know that it's largely a non-explosive, more what we call an effusive type of an eruption. And so by looking at the past, we can predict or have some sureties as to what's going on in the present and into the future. So hopefully that was helpful. From Simmons, does the fact that there's uplift around the area of the Blue Lagoon at the same time as there are fewer earthquakes in the more shallow southwest northeast intrusion further east mean that there's some sort of bottleneck on that route which causes the pressure increase and uplift at one end without a similar effect in the intrusion as of yet? Yeah, that's a really good question. He's or this person, shouldn't assume it's a he or she or they, or is talking about let me add this here. And let's add the power plant in the Blue Lagoon too. That we've been getting that we had the uplift in this area here a few days ago, and that uplift didn't necessarily, we didn't see any evidence that there was magma moving over into this per se. And so is there some sort of bottleneck? Is there some sort of obstacle that's hindering the magma movement from this area over into the dike, into the big intrusive body that's over here? I don't know. That's a good question. I don't know that I can answer that directly. I think your hypothesis is a good one, and there could be a constriction. There could be, we've had earthquakes and stuff, so that plumbing system changes as the earthquakes occur, right? You can get things moving around a little bit. Or it could be that the magma is intruding easily over here by the power plant in the Blue Lagoon, and you don't have sufficient magma pressure to force its way over to the east into that system. So, yeah, that makes sense to me. So, good question. Some of these, I'm doing the best I can. I'll just give you my take on them, and you're welcome to disagree. You guys might come up with better ideas. I'm totally open to that. We're all learning together. From Chris M, thanks so much. Da, da, da. This might seem like a silly question, but could it be that the magma has not breached the surface yet because the top layer is similar to a basaltic cap that you would find in a tuya type volcano? Okay, so this person watched maybe watched my video that came out a few days ago on tuyas, which are these really cool landforms we get in Iceland that form underneath a glacier. As the magma comes up under the glacier, it forms pillow lavas at the bottom because there's still a lot of pressure from the ice and the water sitting on the volcano. But as more and more comes up, lava comes up and melts away the ice, eventually you get a shallower amount of ice or water on top of that, that it becomes explosive, and that creates a different type of rock, like a volcanic breccia, or what we sometimes call hyaloclastite on top of that. And then finally, the vent can erupt on top of its pile of material, free of all the ice and water, and form a nice hardened basaltic lava flow cap on top. Um, I would say, though, in this case, I guess it's possible, because we just don't know. It's a really good question because we can see the surface geology and we can see that there's some of these prominent hills in the area are in fact tuyas or subglacial volcanoes. So they formed when the area was covered with ice. But what we don't have a good handle on, except with a few well logs and data, is what goes on below that, because you literally have several kilometers of rock below that, and we don't have a good handle on the stratigraphy or the layers of rock that are below that. Is it all basaltic lava? Is there some pillow lava? Maybe because some of it might have not necessarily even been subglacial volcanism, some of it might have been lava mixing with ocean water, because a lot of this area on the peninsula is pretty low topography. Um, and so it's a really good question. But it's possible that magma hasn't breached the surface because it's running into a very resistant rock type, maybe a basaltic cap that you find on top of a tuya, as you mentioned, and it just doesn't have the internal pressure to break that rock layer, which would generate earthquakes, and then make a conduit or pathway to the surface. So, yeah, eventually it could. That can change, but right now that might be what's going on. So, definitely not a silly question. I think that's a great question. Brian Hawes, a fellow geologist, retired. Great. Have you been able to find any recent thermal drone data? I'm curious as to whether the surface temperatures have decreased any in Grindavik, possibly indicating the cooling and solidification of the dike intrusion in that immediate area. So the thermal drone thing is exciting. And I know the good gentleman who does the videos at the YouTube channel Just Icelandic has a thermal drone that he's taken up and flies around. Thermal imagery works great when we have an active eruption or lava that's really close to the surface, within like tens of meters. So it is possible that if you flew a thermal drone over this area 4 times a day, for every day for the next however many weeks or months, that eventually you might see in your thermal drone imagery some change along some crack that indicates that the magma is approaching the surface. The problem with right now, the best we know, is that it's just too deep. It's a half a kilometer down. And so the thermal imagery right now, I wouldn't expect it to show anything. You might, and what you need to be careful with too is just because you see a crack out in some old lava field that has a little bit higher heat signature, remember that we have a geothermal system. We have a groundwater system that's being heated by the rocks below, and that hot water is rising to the surface and it generates steam. A lot of you know that if you go to a lot of parts of Iceland, especially this time of year when it's cold, and you look out across some of these landscapes, you'll see steam coming out of the ground. And that steam is not indicating that there's magma beneath it. It's just indicating that the water and the steam in the subsurface is warmer than the air temperature, to be able to see that. So that would be my caution in looking at the thermal data. But if this thing progresses to the point where we think the magma's ascended much closer and an eruption is really imminent or likely, could that thermal imagery be helpful? Absolutely. And where thermal imagery really comes into its own is when you have an eruption that's ongoing and you have these thick gases and steam that you just can't see. Well, like what's going on in the volcano? I can't see through this thing. That's where the thermal imagery will see right through that and show you where the lava is hottest, where it's cooler, where it's maybe breaking out in one direction. You can map lava flows very nicely with that kind of technology. So it's very useful. I just think right now it's not the reason you're not seeing any of the officials in Iceland employing that technology is right now it's not useful as far as we know for right now. So, but it could be useful as the situation progresses. So, great question, Brian. From Bruce, what is all of this ground deformation doing to the power plant physically? Is it built with mechanical flexibility to compensate for all that movement? Well, I don't know, how they built the power plant. I don't know the designs and the structure. I'm sure, though, the Icelandic people are really intelligent. I'm sure when this was constructed, although I don't know when it was constructed, they used the best information they had at the time. They've known for as long as the first people came ashore that the area was volcanically active, that it was seismically active, and I'd like to think that they've built their infrastructure such that it can withstand as best they can those types of forces. That being said, remember that the earthquakes here, we don't expect anything big enough to really cause substantial structural damage. So you would need, we have had magnitude 5 quakes here, but that's pretty close to the upper limit. I don't think you're going to see like a magnitude 7. I'm almost confident of that. A 6 would be really hard to generate too. That would cause enough shaking where you might compromise uh, the the pipelines or the infrastructure of the plant itself. So, really good question. I wish I knew a little bit more. But as far as I know, the geothermal power plant is operating just fine, and it probably sustained some minor damage from the earthquake swarm a weekend or so ago, around November 10th, 11th. But I don't think there was any substantial structural damage. So I think that they were able to withstand that. From this person, sorry, I can't pronounce that. If the magma is from a deeper source, is that bad? Because it may travel further or erupt with more force. No, magma is pretty much magma. So it doesn't matter if it's magma coming from a deeper source or if it's shallower magma. Um, for the purposes of volcanic eruptions, it's going to behave largely the same. It's just going to be a question of how much dissolved gas does it have, how much magma is there, um, where exactly is it erupting. Yeah, so the source, the only reason the source might be bad if you had a deeper source is sometimes deeper sources can supply you with a larger volume of magma to the surface versus if you have a shallow reservoir. Usually the way this works is that there's a bigger chamber of magma deep and that feeds a shallower body of magma, and that shallower body is the one that drives the eruption. But if you have a more of a connected path from the deeper source through the shallow source to the surface, then sometimes that means very large volume eruptions. So I don't think we have enough data to know that just yet. But once the eruption occurs and we're able to look at the rocks themselves, actually get a sample, of the lava, there's things they can do with looking at some of the crystals and how the crystals grow and develop that tells them the ascent rate of the magma as it moves through the system. So there's really cool stuff they can do on that end. From JF Mezzi, as magma rises, its pressure is reduced and gases undissolve. Okay, that's true. And the bubbles cause expansion of magma, which now has greater quote unquote motivation, right, to rise. It's more buoyant. Okay, right? Question mark. Yes, good job. Is it possible that the ground above would be strong enough to not only pause the magma's path, but also hold a pressure high enough to stop release of gas bubbles, keeping the magma more dense and less need to expand? Yeah, great question. So it's all this density buoyancy thing, right? The magma has buoyancy and density of X. The surrounding rocks have a density of X, and it's really just this game, right? If the buoyancy of the magma and its upward pressure or force is in excess of the pressure trying to keep that magma in the subsurface, then it will rise. And so it's possible the ground above would be strong enough to, yeah, absolutely. The ground, the rock above and on the sides of that magma body could definitely be strong enough to pause its ascent, and the gases are just in dissolved in with the magma. As the magma rises, though, those gases will tend to come out of solution and expand, which means the whole magma body needs to expand, and that's where the pressure comes in. Hopefully that helps there. Or do vast majority of cases always result in magma finding a path to the ground? No, there's plenty of instances. We probably don't hear about them as much, so it's selective bias probably on our part as humans, that a volcanic eruption, well, that's exciting. How many people tuned in and did a deep dive on magma that stayed underground forever? Well, that only the scientists really study those sorts of things. So, but there are plenty of cases, I'm sure, where that's been the case, and we can see that in the rock record as well. Tim Berry, could the lack of earthquake activity under the power plant and Blue Lagoon be due to hotter, more ductile rock deforming rather than fracturing? Absolutely. So the idea there is that we're seeing the uplift, the recent uplift of the power plant area, um, and without earthquake activity, possibly because we've already injected magma under there. We already had a bunch of quakes there previously. Um, and now that rock is hot and more ductile. Remember, earthquakes only occur when rocks break. And so if the rock is hot and able to bend and flow without breaking, then you're not going to see the earthquakes or the seismic signal there as much. So if we don't see earthquakes there, you can still have magma moving into the system. Um, if we started seeing earthquakes around the power plant in Blue Lagoon, that might mean, especially if we could track the depth going upwards, that might mean that magma body was forcing its way upward in that location. So um, I would assume the geothermal plant would be constructed over the hottest rock in the area. Yeah, generally what they do when they site a geothermal power plant is they drill test holes, and they're looking at the rock somewhat, but more importantly the water. So you got to have water of a certain temperature, and I don't know a whole lot. I'm not an expert on geothermal plant development, um, but that would be the idea. Is you've got to, and shallow too, right? If you have to drill down like a kilometer to get to the hot water, sometimes those really deep, maybe that's not that deep, but if you have really deep resource, that can be a lot trickier in terms of generating the electricity as opposed to something that's shallower. And then our final question, hopefully this has been helpful to you all. I've enjoyed it, so appreciate the questions coming in from Jennifer McMillan. And this is probably a good, appropriate question to end on. So what would happen if this did continue to erupt for 300 to 400 years? So the idea there is that we've got a history of eruptions on the Reykjanes Peninsula. And what if this eruption that began in 2021 over here, and we've had 3 eruptions there, what if we get something else happening in the near term in this area? And what if this region, just collectively on the peninsula, continues to erupt for several hundred more years? Um, it's a great question, and it's probably something that, long-term thinking in Iceland, they should probably consider, is if this area was settled during a quiet period in its volcanic history, and if it suddenly springs to life and we see on and off eruptions that go on for hundreds of years, what would that mean to these folks? It might mean making some really drastic changes. I don't think we've seen anything like this in definitely in modern history that I can think of, where you take whatever percentage of Iceland's population is here, and I know it's most of its population, you might need to displace all these people and all this infrastructure to some other area in Iceland that you deem is less likely to be impacted by volcanic activity, whether that's up here in the West Fjords or somewhere in the north part of the country. Um, Really good question. Lots of implications, and probably a bigger uh, issue that would involve lots of people coming to the table and looking at the data and making hard decisions. And the way it would probably play out would be um, you know, incremental changes, right? Like let's assume and of course we hope this doesn't happen, but let's assume this geothermal power plant just can't be here anymore because we've got volcanic activity. Well, we know they're already drilling a new water well over here for cold water. And it's possible there is another power plant down here. I don't know much about it or how much it serves in terms of area, but they have other geothermal power plants. So maybe it's just a case of switching these communities over to a different energy source. And then we get more volcanic activity here. So we've slowly moved our infrastructure out of this area, or we're not reliant upon this region anymore, and we're relying on other areas. But as the volcanic activity continues, it's really a matter kind of where it's at. If it stays along the south coast, I mean, other than the power plant and Grindavik, which are the two most crucial areas here, most of this coastline, there's a few farms, and there is another town over here, but pretty uninhabited. And so you could have quite a bit of volcanic activity to the south that really wouldn't have a huge impact on Iceland. If the volcanic activity, though, shifts towards the northern part of the peninsula, that's a whole different ballgame, because now you're impacting Keflavik, the international airport, and possibly even the greater Reykjavik area. So anyway, interesting thoughts and questions there. Okay, so that was it for the questions. Hopefully you enjoyed that. If this is something that's popular, it's something I'm open to doing again in the future, especially on days like today where there's maybe not as much happening with the volcano, a little bit of a lull in the activity. We might as well spend a little bit of time learning together, becoming edified, educating ourselves, hopefully generating some good productive discourse and discussion. That would be great. I'm going to continue to learn. I've got a textbook that I'm reading that I just ordered, Volcano Tectonics, which has a lot of stuff I'm interested in diving into about dike propagation and yeah, all sorts of stuff. Pretty heady book, but I'm going to wrap my head around that, curl up with a warm blanket and a hot beverage, and that's my evening probably. So anyway, hope you're well. Thanks for all your support and encouragement. Thanks for continuing to tune in here. I appreciate it very much. Keep the questions coming. If I'm not addressing your question, I apologize. There's definitely a volume in terms of how many comments come in. It's great. The success of everyone jumping on board is great, but I only have so much bandwidth to cover that. But know that I am reading all your comments, even if I'm not answering them all. So appreciate your time today, and have a great day. Take care.